Okay, I would like to give a second characterization for power spectral density. So let's get started. A second characterization for, let's say, Sx e to the j omega. So what was our previous characterization? We were thinking that we have a filter, and this filter has a narrow pass band. It's a band pass filter with a very narrow bandwidth, let's say. And then I am filtering my random process through this band pass filter and checking its output variance. Okay, process variance. So I know that the output process will be Weiss and stationary. I'm calculating its variance, and that becomes the power spectral density as the bandwidth of the filter approaches 0. Okay. Now here's the second one. This is also very important, but this is a little bit less used than the other one. So this is, let me see. It's a little bit different than the earlier one, but I think it will be clear. My random processes, x of n. Okay. So over here, this is the window function. So this window is selecting 2n plus 1 samples, let's say, around to 0 index. Okay. So n is this n, so this is the positive side support and negative side support. So beginning and the end of the support of this window for this n variable. Okay. So what else? So then, if we have such a case, so this is obviously dTFT. Okay. Then power spectral density is equal to okay. So what's going on? Well, I have a random process. So this is the end of the statement. Let's say that this is one of its realizations, and I'm thinking again in terms of ergodicity. We will discuss ergodicity later on. So I'm taking its samples, as you see. So I'm taking, let's say, 10 samples, or let's say 11 samples. Because from -5 to 5, let's say, then I get 11 samples over there. So these are the samples in this window. So if I calculate, since it's a finite length sequence right now, its dTFT is always defined. No problems with its definition. Let's say that I'm interested in the 0 frequency, then omega is equal to 0. I'm calculating the sum of these samples. Okay? So at a specific frequency 0. Now I calculate the sum. Then I make this window larger, 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 larger. Now you can say that there can be a divergence over here because you are getting an infinite summation and so on. Indeed, you are right. Okay, this will be diverging. This is the reason that we have some normalization over here, but let's do not focus on that. Again, we are calculating for larger and larger windows this dTFT value at a particular frequency, and this result says that as the number of the samples, window length, goes to infinity, then this random variable, if the DC frequency, sum of all the samples, okay, so divided by this, normalized in some sense, this random variable will be, the power spectral density definition. Okay. Well, this is not very surprising because you may consider this some kind of a, for the DC frequency at least, some kind of an averaging operation as some kind of filtering again. Okay. So again I'm doing some kind of a filtering, but this is not exactly filtering. This is like windowed Fourier transform calculation. and I'm evaluating this windowed Fourier transform calculation at a particular frequency. So this is at the beginning a little confusing because xn e to, or x e to the j omega, let's say. Now I have a random process and I'm calculating its Fourier transform, as you see, minus infinity to infinity. Okay. So there are some issues about this, but okay. So how about this? If I fix my frequency to omega naught, as you can see, this is nothing but weighted sum of random process values. Okay, sampled random process values. So this is nothing but a random variable. Okay, so for every frequency I have a random variable, but as you can see, this is a continuum. Okay, there is a continuum of omega. Okay, so actually omega, i.e. omega is in between in signal, in this discussion. Let's say 0 or 2 pi, minus pi to pi, etc. So indeed, you may think at a fixed value, it's like a random variable. How about this? This is also a random process then. So this is another random process. This is the reason it's a little confusing. With process variable omega. Okay. Of course, as before, for every random process, if I fix this process variable to a, let's say, value to a omega is equal to pi over 4, let's say, then I get a random variable, as we have discussed before. So then, this is making a little bit more sense. So at a particular frequency, I calculate this variable's variance, okay, the variance of that random variable, and then normalize it, I get this power spectral density. This is again not very easy, not very difficult to show, but I'm not showing this result. I'm just making you somewhat aware of this result, and that is sufficient for our purposes. Okay? So we have a second characterization like that. So there is important discussion about, how should I express this? The relation between White-Sand stationary processes and Fourier transform. White-Sand stationary random processes and Fourier transform. Okay. So this is something maybe you will, after our last discussions on decorrelation, you will appreciate a lot better, I guess. X e to the j omega. Again, I'm writing the same thing. Minus infinity to infinity. Okay. So let's say that this is a random, well-defined random variable. Okay. Now the question is, assume x of n is zero mean, as we did all the time. Random process. I'm not interested in the mean actually. Okay. And calculate the covariance of x of e to the j omega 1 and another frequency, x e to the j omega 2. Okay. But zero mean and White-Sand stationary. Okay. Zero mean random process. Zero mean and White-Sand stationary random process. So the question is, find the following. Find covariance of this, two samples. So how can I do this? Actually, the end result is interesting. You will see that the Fourier transform is decorrelating every White-Sand stationary process. So it's like decorrelating transform. This is the reason that there is a large interplay between Fourier transforms, autocorrelations, power spectral densities, etc. Okay. So let me explain this. So what is covariance of x? This covariance, let me write this bigger. Okay, so this is expected value of, since these are zero mean quantities right now, I can calculate autocorrelation. Omega 1, this is conjugate. As you see, these are regular random variables. I'm calculating their correlation right now because both of them are zero mean because of our initial assumption. And as we have discussed many times, mean is not the critical thing in this discussion. Okay, so then I will include this definition, but I will move two summations. I have an n1 summation, I have an n2 summation. So let's move this expectation in. X of n1, x conjugate n2, so this is then e to the j omega n1 times e to the minus j, this is omega 1 I guess, omega 1 n1, omega 2 n2. Okay, so I insert instead of omega 1, and I use dummy variable n1 over here. So n1, omega 1. Do the same thing for omega 2, and I use n2 for that one. There is a conjugate for all two variables, n2, omega 2. That is it. Now, this is our autocorrelation. But since this is White-Sand stationary, this is Rx n1 minus n2. It's a function of a single variable, okay? Because this is White-Sand stationary, as we have said. Now, how about this one? This is, let me change this. Doesn't matter that much, n1, n2. Now, let me calculate this bracket. This is the Fourier transform of Rx something, and I'm taking its Fourier transform with respect to what? So this is from n1 to omega 1, isn't it? But maybe I should, again I have changed my mind, sorry, because of this minus sign. Okay. Let me then write this one more time, n1, n2. So I want to do it for n2 first then. So this is n1, n2, Rx, n1 minus n2, e to the minus j. Because I want to use the simplest relations that we know. Okay. So I just move this in, take this out. Okay. Now, what is this one? Fourier transform of this with respect to n2. Okay. So how can I take the Fourier transform of this one? First, I change again one more time variables. Sorry for the confusion, but this is just, n2 prime omega 1 n1. Okay. So n2 prime. Again, n2 minus n1. Sorry for this. Then let me do it this way. I think this time it will be fine, hopefully. Now, if I change this variable to, if I call this dummy variable, let's say n2 prime, okay? Then n1. These are all minus infinity to infinity. Okay. So n2 prime is also minus infinity to infinity because you can check when n2 is this, n1 is fixed. So this is again minus infinity to infinity. So this is Rx n2 prime e to the, now instead of n2 minus j omega 2, n2 is equal to n1 minus n2 prime. Okay. E to the j omega 1 n1. Okay. Then, if I do this part, I get N1. So this is now the Fourier transform Sx e to the j omega 2, but with a minus sign over here. Okay. E to the minus j omega 2 n1. So this is this bracket. E to the j omega 1 n1. I get something like that. So why do I have this minus over here? Let me see. Rx n1 minus n2. Because of my earlier mistake over here, I guess. Because this should be minus. Then this is the Fourier transform definition. This is minus. This was causing me the, difficulty, I guess. Okay, let's check this. This is the Fourier transform definition. This is correct. This is correct. Now I insert over here. This is correct. This is correct. Now n1 has minus sign. N2 has, maybe I don't need these steps anymore, plus sign. Okay. Now I do this variable change, n2. So this is plus. This is n1 minus n2 again. Okay. This is minus. This is this one. This is again plus. Sorry for this. But, okay, good news. Now Rx, this, and I have to take this one out. Okay, this is this. E to the j omega 2 times n1. Then I am left with e to the minus j omega 2 times n2 prime. Okay. And this summation becomes a power spectral density definition, as you see. Okay. So this completes this bracket. And what I have is this. Now, this is plus Sx e to the j omega 2. Now I have the summation. Sorry. N1 e to the j, let me see, omega 2 minus omega 1 N1. Okay. So about this one? Well, if you wish, I can put a minus sign over here, and this will be plus minus like this. Omega 1 minus omega 2. So what's the value of this summation? Okay. So this is nothing but the Fourier transform of 1. With, Fourier, this is just 1. Where the spectrum variable, Fourier domain variable is omega 1 minus omega 2. So this is 2 pi delta omega, well, Fourier transform of 1 is delta of, just delta. Delta omega 1 minus omega 2. Okay, so this is the impulse, and this spectrum variable, whatever this is, when this is equal to 0, I have an impulse. That's when omega 1 is equal to omega 2. So what do I see? I see the following: Sx e to the j omega 2. There is a 2 pi delta omega 1 minus omega 2. Okay. So what's the conclusion? The conclusion is very interesting. So what we see is the following. Samples of white sand stationary process in spectrum, that is x e to the j omega 1 and x e to the j omega 2 are uncorrelated, because as you see, their covariance is equal to 0 unless these two sampling frequencies are the same, are uncorrelated. Of course, I'm assuming omega 1 is not equal to omega 2. Okay. So sometimes, hence, the process in Fourier domain is very interesting. The process in Fourier domain is non-stationary white noise, where process variable is frequency omega. Okay, so this is our interpretation. As you see that the covariance of these two, it's when omega 1 is not equal to omega 2, it's always equal to 0 because of this simple calculation. And this is valid for all Weissan stationary processes. And furthermore, what we see is if this is like a Gaussian process, then this process, Gaussian process, when Fourier transformed, the samples of its Fourier spectrum, such as this one, they're independent. Okay, so we get very strong results. Okay, so by transforming a Weissan stationary process to the Fourier domain, essentially I am decorrelating the process. So Fourier transform, as we have previously studied it, it acts like a decorrelating transform. Okay, it decorrelates, so it is aligning, you may say, for the Gaussian distribution, it's aligning the axis of this probability distribution with the axis of our representation. Okay, so Fourier transform is doing that in an abstract sense, of course, because this is like an infinite dimensional operation right now. Okay, so this is an important bit of knowledge. So we have made a silly mistake over here, but I think we have recovered it at the end. So that's all I would like to say. This is also an important result to remember, the relationship between Weissan stationary processes and the Fourier transforms. Okay, so we will continue with more discussions later on.